All right, it's close enough. Hey guys, my name is Aaron Alt. I'm with the Open Ag Technology and Systems Center at Purdue. For those of you who don't know me, I'm a farmer in north central Indiana. I've got about 3,200 acres of corn and soybeans, and then 3,000 head of beef cattle, and that's my day job. And the rest of the time, I'm a software developer and co-founded the OATS Center here at Purdue. So just quick show of hands, how many people here, your job is primarily like technical coding sorts of things or IT kind of stuff? Yeah. And how many is it primarily like business, sales, or just agronomy, that kind of stuff? Pretty even split. Okay. Well, hopefully this has something for everybody here. Blockchain kind of came on the scene about 2012 with cryptocurrencies and things like that. And there's this odd property that it has. It's called the 364% effect. I coined it. That there was a company that had nothing to do with blockchain that changed their name to blockchain, and their stock went up 364% the next day. There's this sort of hype factor associated with it that tends to get me places to go talk that I wouldn't have perhaps spoken at before, like Lions Stadium for Siemens. That was kind of cool. But what I try to focus on when I give these talks is really what is it? Because I find if you go try to figure out what it is and what's it good for, you find a whole lot of stuff about how it's going to change the world, and they stop before the punchline about exactly how. And so we're going to talk today. The first half of this is really going to be what is it, and the second half is going to be an invention that we've had at the OATS Center as an extension of our Open Ag Data Alliance and Trellis projects. That really solves a fundamental problem in most blockchain installations. I think you guys are going to find it pretty interesting. So let's kick it off. There's two questions to start with. One, what problem do most people think blockchain solves? And the second one is, what problem does it actually solve? So I took the time on the way here on the plane to kind of come up with some personas of the folks that I encounter in the blockchain world. The first one I call Pac-Man. Blockchain, 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 blockchain. That's just every word out of their mouth, blockchain. And you say, I don't know, but it's going to change the world, man. You know, like it's where we're all going. You'll see those guys a lot. Another one I call Joe Q Ponzi. He's just, I don't know, it's just something about cryptocurrencies. You know, I've made a lot of money doing it. And you say, what are cryptocurrencies? And he's like, well, it's free money that's so cryptic, nobody understands where it comes from. So you should join in. And bam, hockey stick graph. Trust me, you'll get rich. You know, there's plenty of those guys in that space. There's also the Bank of Satan. You know, evil needs savings too, and they need it to be anonymous, self-cleaning. So, you know, North Korea and a lot of other folks that aren't always doing things that are on the up and up tend to use it to shift money around in ways that they think can't be tracked. And then the one I encounter the most, I call the Enterprise Kid. It's really about transparency. That you know, privacy doesn't tend to enter into the equation too much. It's sort of just, well, why shouldn't our competitors see right through us? Transparency is what we're looking for. Blockchain is safe. Hey, sustainability, it's for the children. If we don't do this, we're all going to die of food poisoning. That's kind of how it sort of boils down in a lot of these conversations. And I think what gets missed, and thankfully there are some folks out there with this message, but the thing to take away from this talk, if you take nothing else away, is what blockchain really is, especially in the enterprise discussions, is just about sharing data across company boundaries. That's it. It's a shared database. It's a place we are all going to agree to put data. That's it. So what problem does it actually solve? Or another way of coding or of phrasing this is, why don't we just use MySQL? I mean, if it's just a shared database, why don't we just stand one up that everybody knows how to use and start putting stuff in it and pay somebody to manage it? So blockchain was designed to solve originally with Bitcoin to solve something known as the Byzantine generals problem in the computer science field. And there's actually nothing really Byzantine about it except it's just a memorable term. It was originally put forth in this paper in 1982 by Leslie Lamport, Shostak, and Peace. The basic idea was, imagine during the Byzantine era, you had a group of generals all camped around a castle. And they can't really talk to each other except via means of sending messengers, right? Like, so each general lives in each camp. They each see a slightly different part of the castle. And so they each have slightly different information. And they all have to decide, are we going to attack or retreat? And they decide if we all decide to attack, that means we've all seen enough of our vantage point that we think we're probably going to be successful and win the day and we'll capture the city. And if we all decide to retreat, then we'll probably get away with our lives, or at least most of us. But if we don't agree, like some of us attack and some of us retreat, we're probably all going to die. So we have a very vested interest in making sure that we reach consensus. And so if you think about, well, how would I do that with messages, right? Because like the courier can, get killed along the way. Messages can get captured and changed, all kinds of stuff. That alone is a hard problem. Even if you assume the couriers themselves are valid, because one thing you might come up with originally, or just thinking about it a little bit, is you say, well, okay, what if we just all put our vote on an envelope? And if there's 8 of us or 9 of us, I'll put my vote on 8 other envelopes, and I'll send couriers out to everybody else, green check mark or red X. And then they'll all send me theirs, and I'll write down all the votes, and I'll change my vote to the majority, and then I'll send my vote back out. And we keep doing this, and eventually we should all kind of approach consensus where all the marks on my paper are check marks. And that's tough because, like I said, couriers get lost. How do you know he didn't get there? There's an infinite hacking problem. But that's not the Byzantine general's problem. The Byzantine general's problem is what if one of these guys is a traitor? So he's working for the other side, and he sends half yes votes and half no votes. And he can prevent us from ever reaching consensus, so we essentially just all run out of supplies and starve. He can actually trick us into half of us attacking and half of us retreating, and then he ends up, getting rewarded by the enemy. That's the Byzantine general's problem. If you are not solving a problem that doesn't have potential traitors, you don't need all the overhead of a thing that solves the Byzantine general's problem. So if you trust everyone involved, blockchain is a little bit much. MySQL is a whole lot easier. If you don't, then it's time to break out some of the blockchain. And you'll see later on there are some pretty good use cases where it does present a pretty nice solution. And so I've got this nice tutorial. It's at this particular URL. So you can go here. It's open source. All the code is up there. It's in GitHub. You can pull it if you want to. Show your friends. That we're going to actually go through how does it achieve that Byzantine fault tolerance. Now let me mirror my display. All right, can you guys see that? A little hard to make out, but I think we're close. Let me make this a little smaller. All right, so you guys can go there and do this if you want to. We're going to actually build a blockchain in our browser and see under what conditions it works, what conditions it doesn't work. And we're going to do that in the context of food traceability. So right here, these are a few of the things that you would find on a traceability label in the food industry, put out by the Purdue Supply Organization, for example. That you might see that actually on a package of grapes that have a little label. It's got a G10 and where the country it originated at, what it is. I'm going to add some stuff in here from our Trellis project as well. The idea here is that this particular product or this lot, it may have some other private data at this URL. And here's a hash of that data, which we're going to get into in a minute. But it means that if you have permission to go view that later, you can pull that from here and go get that data. But it's not something we've released to the world to see. So each one of these little labels, we're going to add this to. And we're going to essentially say, we want to keep track of a database where traders may or may not be in place. But we still want to have a good database of all those so that when the consumer goes to the store, they can trust that the package that has the label on it is actually authentic and it hasn't been messed with. And so one of the first ways to do this, actually, I saw a legal company that did this, is you could just simply publish this thing in like the Wall Street Journal, okay? And then expect all of your customers to carry the Wall Street Journal with them to the store. And then when they get the label, they'll open it up and compare your classified ad to that, right? That's a nice low-tech way of ensuring the authenticity of the traceability data on that package. It's also very expensive. And so you'd like to maybe reduce the number of, you got pay per character in those things. You want to reduce the number of characters. So you say, hey, we may end up with a lot of stuff in this label. Can I come up with some shorter thing that if I change the stuff in the label, the shorter thing changes? So like you see this string down here? If I type up in here, you see it's changing as I'm typing. We're going to call this thing a hash. And if I asked you, well, how would you create something like that? You might come up with something like this. You say, well, look, I'll just take all the characters, all the letters that are in the message itself, and I'll just put them all in columns, right? So there's the G, the T, the I, and I'll make it like 10 wide or so, and I'll just line them up. And then I'll trade each of the letters for a number. So there's just some code, like a capital G is a 71, a capital T is a 84, and so on. You can't read the numbers at all in there. Let's see if we can make that a little better. Yeah, you can read it. And so then if I just add up all the columns, like throw away the carry bits, and then convert them back into into string characters, just like we converted to numbers, I'd get something like this, right? So you see as I add stuff, it's going to get added onto the bottom of this thing, and it's going to get added to the number, and we get our total sum here, and it ends up changing the hash. And so now I can just publish that hash to the Wall Street Journal. I'm so zoomed in, I can't even find all my buttons. There we go. So I can publish that hash to the Wall Street Journal, and then like your consumer can go with their Wall Street Journal and their app, and the app can scan the tag, and it can compute the hash, and then they can look at each of the characters and line it up in the Wall Street Journal. But even that's pretty expensive, right? They don't have enough classified ad pages for all the traceability labels and all the produce in the entire world. So we're going to make one slight modification to this and say, well, all right, we've got traceability label number 2. And instead of me having to put a hash for every one of these labels in the Wall Street Journal, I'm just going to take the hash that I got from the first one right here, and I'm going to make it part of the thing that I hash in the second one. So if I change the first message, you see the second hash actually changes because the thing is propagating on up to the top box up there. And so when I do this, I've chained the blocks together, hence the name blockchain, so that I can actually just publish the last hash in the chain. And now when they go check with their thing, I only need to take one classified ad out in the Wall Street Journal, and they can check any of these things along the chain and know that none of them changed, because otherwise the hash at the end would be wrong. And you think this sounds really inefficient, but there was a company out of New York that this is what they did for legal documents. They would ask you to hash all the legal documents in your case. They would take the hashes of all of their customers, they would hash all of that, and they would take out an ad in the New York Times, and they would prove that your data was that as of that day. And they made a lot of money doing it too. This was in the days before blockchain. So there's several problems we still have though, and we'll get into each of them. But the first one we're going to tackle is, well, how do I know that the bad guys didn't just put that message in there and not the good guys, right? How do I know who's allowed to register these things in my database full of all of these traceability labels? And so that's where we're going to get into digital signatures a little bit. I have to zoom out a little bit. So the basic idea is that anytime the blockchain or a database or anything in the digital world has to interface to the physical world, there has to be a human oversight. It is flat out impossible to guarantee that a connection from the digital world to the physical world is absolutely correct in all cases under all malicious actors. So no matter what, somebody somewhere is going to have to certify who gets to put these things into the database. And the way they do that is you say like, well, one of the auditors out here, or one of the people that we know raises grapes, let's say, he's going to have a password that only he knows, which is the word password, which is the most used password in the world. It's probably a bad choice. But the mathematicians, thankfully, they've come up with this really cool math it's not too much different than this hashing thing that you've seen here, right? We're going to take messages, we're going to take characters, we're going to turn them into numbers, and we're going to do a little bit of multiplication on them. But we're going to end up with a string that you can only generate this string if you know this message and you know this password. If you don't know the password, it's effectively computationally infeasible to figure out what this thing is. And so those sorts of strings look like this. So this is actually using the signature algorithm that Bitcoin uses. Now, that alone is not useful, because in order for that guy to essentially tell, for the consortium to distribute to everybody who are all the trusted players, you would have to know the guy's password to check, did password actually get used to create that signature? So the mathematicians gave us this really cool thing called asymmetric cryptography, which says we can take the password and we can compute another really long thing. We're going to call that the public key. It has a property that if I give you this really long thing, you can't figure out password from it, okay? So you can't derive the private key, the password, from the thing I gave you. But if I pass the message through the function with the public key, or the signature through the function with the public key, I'll end up with the hash of the message back. So it means this public key can be used to validate that this signature was created with whatever password gave rise to it, but we don't know what the password is. So I can create a trusted list of places that says, here's all the public keys of everybody who has passwords who are allowed to sign things. Now, if one of them is password, that's a bad idea. So thankfully, the mathematicians gave us better ways to come up with big random strings. So here we'll compute a great big private key, one particular public key. We'll sign this document with it. Now, the text in this is still red because I haven't added this thing to my list of trusted signers. I don't know that this guy generally does produce grapes. So if I go ahead and save that in my list of trusted signers, now it's super fast to validate these signatures cryptographically to say, all right, I don't know what the password was that made it, but I know it was on the list of people that were allowed to put things into this chain. So that solves the first problem. So we can go ahead and sign each of these things. And then that gets added as part of the stuff that gets hashed together. That's the only way, to the best of my knowledge, to essentially figure out that only trusted people are allowed to put stuff in. Okay, you've got to have some kind of a public-private key consortium together. And so you'll see things called permission blockchains that basically do this. There's some governing body that sits around and hands out the private keys to them and say only you are allowed to post stuff into our blockchain. So that's the first step. Now, the next step is that let's say we add a couple of peers in this network. All right, so we're gonna have a couple more computers in this network that's all maintaining this particular list of stuff. And one of them may end up being a traitor, one of them may not. But in order for our overall algorithm to work, we've got to introduce two new concepts. So the first concept is the idea of a correct hash. So we're gonna say, I'm not gonna allow you to actually put a hash, like none of these other two guys will accept a block in their chain when the other guy sends it to them, unless it's got a hash on the bottom that starts with a certain number of zeros. In blockchain, it's 40, I think, now, or something like this. We're going to pick 4 because we don't have centuries to sit here and chug away at it. But we're going to say a correct hash has to start with 4 zeros. And so that means I'm going to have to add something here, a number that I'm going to add to the original message to get a hash that starts with 4 zeros. And now, if you're using my little sum hasher, the thing that just adds up all the stuff, it's really easy to figure out what to add to the message to get a hash that starts with 4 zeros. It's just the negative of the sum. And voila, I get a hash of all zeros. It's really easy. And so that's kind of why we should use a hashing algorithm it works roughly the same way. Like we have columns of stuff, add them up, but it like rotates things around. It replaces 61s with 64s. It does a bunch of things that seem completely random, but the cryptographic community has shown that essentially that algorithm, to the best of our knowledge, is non-invertible. You can't take a hash and guess the message that gave rise to it. And that's called SHA-256. Now, to give you an idea, so here's how we'll do it. We'll try 0. We got a hash C945. That's not 4 zeros. We'll try 1. That's not it. We'll try 2. We're going to be here a while. I'm going to hit the mine button. It's just going to count up until it finds one. There we go. 95,123. Now, to give you an idea of how hard this problem is, since no one knows how to take the hash and get the message, a 256-bit hash has roughly 10 to the 77th power possible values, okay? There are 10 to the 60th atoms in the entire observable universe. So that's starting from our point in space and going out as far as light could have traveled since the beginning of time in every direction. And we count all the atoms, we'll get 10 to the 60th. If we count all the elementary particles, like neutrinos and everything, we're going to end up with about 10 to the 80th, according to physicists. So the problem of just guessing and trying to get a message that gives you the exact hash you want is equivalent to painting an electron green somewhere within 14.5 billion light years in every direction and asking you to go find it. It's basically impossible. And so that is the fundamental thing that we say, no matter how malicious you are, you cannot fix that. Like, you can't game that system. You still have to guess just like everybody else on how to do it. And so since you see these blocks are chained together, this one may be green, but in order for me to get that one added, I'm going to have to go ahead and count up and find the first one that's got 4 zeros there. That one was pretty quick. That one, that's getting pretty quick too. Sometimes they're in the hundreds of thousands. But if I constrain the space even farther, then you're just sitting here for centuries before the thing actually finds it. So this is literally what mining Bitcoins is. It's guessing numbers until you get a hash that starts with 40 zeros. And that's the fundamental thing that secures most, especially public blockchains. Now, the second thing that we have to introduce is the idea that the correct chain, so we've got 3 chains among these guys right now. The correct chain in the network is the longest one you've ever seen. That's the second concept we have to have. so that if this guy tries to publish his chain to this guy, he won't take it because he says, I've seen a chain that's 3 long and you've only got one that's 1 long. So if I go here and I publish, all 3 of those guys will go ahead and accept it, and we kind of have a convenient starting point. Now, the current blockchain network around the world, I think, is consuming somewhere over the 1%, 1.5% of all the electricity burned in the entire Earth on guessing these numbers, which is a lot, and that costs a lot of money. And you might wonder, well, why would someone bother to waste their time doing all of that, burn all those electrons? Well, to do that, we're going to have to introduce a fake thing that we just made up called a Bitcoin. And we're going to say, among these 3 peers, whoever's the first one to guess the hash, I'm going to award them with 12.5 Bitcoins. So if they can guess it first and get it pushed out to everybody else, they'll now have the longest correct chain, and they'll win 12.5 Bitcoins. If 12.5 Bitcoins are worth about the price of a pack of bubble gum, then nobody's going to do this. If a Bitcoin is worth about $10,000, then when this guy wins, he gets $120,000, right? And so then now we're talking some stakes that matter. And so I should actually try to do this for a while. And so that's exactly what happens here. When he guesses it, he has his own private key, and he creates a signature of it with his private key, and he puts his public key on it too. And so if I look through the whole chain and I add up all the blocks, the valid blocks that have that guy's public key on it, I can add up how much Bitcoin he actually has. So what you're going to see in a minute is I'm going to start all these guys racing against each other. They're all going to try to be the first one to win the $120,000, and their tallies are going to be up at the top right here. We might have to zoom out far enough, though, that you can't see it. I'll turn off a few of these other things. All right. So here we go. They're off to the races. Now, this guy at the top, he had a head start. He's at you can't even see it, can you? He's at 87.5 Bitcoins. The guy in the middle, 62.5, 75. The guy on the bottom is 25. He's kind of lagging behind. 112. Oh, now they're caught up. The guy in the middle surpassed him. You see, they're each randomly guessing numbers. So they all have an equivalent probability of being the guy that's going to guess the first one and essentially validate that next block and push it out to everybody else. So you can see, if I'm a bad guy now, I'm going to turn on cheating. I'm going to let this guy cheat. And I'm going to come back in here a ways, and maybe this thing of strawberries from the United States. Oops. See, where was I at? We'll go back here a little ways. There we go. Lettuce from the United States. I'm going to say it came from France instead. You see immediately what happened, that when I change something in this chain, because all those hashes go back and forth between them, then all the stuff on the rest of this guy's chain goes red. All the hashes are now bad, and he has to start the process of guessing numbers again. So when I zoom out, you should kind of see the task ahead of this guy, that before these guys are going to allow his chain in as the longest chain, he's going to have to guess his length is 17, and they're at 25. So he's got to guess 8 things in a row, effectively, faster than they can guess all the other ones. But they're both guessing together, right? So since they're guessing together, they get twice as many guesses as he does. So when I start this race, this guy will get a few blocks. He's not going to always, never be able to get his stuff. But every time he gets a block, he's going to try to push it out, and these other guys aren't going to accept it because it's not long enough. So he's up to 22, and they're at 34, 35 or so. And so essentially, we let this go forever because they have twice as many guesses as he does. He's eventually going to fall hopelessly behind. However, if I bump up his processing power, so let's give him 10. Theoretically, he only needs 51%, but we'd be here a long time. So I'm going to give him 83%. So he gets 83% of the processing power of all the nodes in the network now. And now you see he was at 29. You see he's kind of chugging along pretty quick. These guys are still there. They got 1 or 2. He's up to 38, 39, 40, 41. We're close. The other guys are 41. There we go. All right, it went through. So now I'm going to go ahead and search for France. And you see that the word France, the bad thing, is now actually replicated in all of the 3 nodes in the network. So with every Byzantine fault-tolerant system, there's always a failure condition. If 100% of the participants are traitors, essentially we're all going to just throw down our arms and go live with the guys in the castle, right? And so there's always some condition under which that it fails. And it's important to know that if you're getting into any sort of blockchain initiative is, well, what is the condition under which it fails? Does that matter in our particular scenario? And so this one is called proof of work. I'm proving that I did the work to guess all those numbers. And the condition under which it fails is if somebody gets 51% of the processing power. So that means somebody has to control roughly 3/4, that would be, of all of the electricity on the globe, that total, in order to be able to actually get 51% of the processing power in the global blockchain network. So that is blockchain. That's how it works, and that's why you're supposed to trust it. Is the algorithm is so hard, nobody knows how to break it, to the best of our knowledge. But you'll see a problem with that. One problem with that is all the data and all these nodes is shared everywhere, right? So if you're like a middleman in a food supply chain, let's say, and the part of your secret sauce is who you buy from and who you sell to, right? Who are your suppliers, who are your vendors, and you're asked to put in a public shared database all the people that you buy and sell from, then the guy who's buying from you doesn't care about you anymore. He'll just go to the guy you're buying it from, cut you out of the middle. And so the industry has this fundamental tug of war between the guys on the end that would really like to know a whole lot about all the people supplying them stuff, and the guys in the middle that are trying to do their best job of supplying it, but protecting themselves from the guys that have a whole lot more data scientists on the other end. And so blockchain has sort of become this proxy in the food industry for transparency. We're all going to publish everything that we have publicly to the world, or not to the world. It's a permissioned blockchain. So it's published publicly to everybody in the blockchain, which is supposed to be everybody in the food industry if it actually takes off. And so that's a problem, right? Like most companies don't like to just put all of their stuff up publicly in some kind of a shared database like that. Let's see if yeah, there we go. So that's where Trellis++ comes in. This was an invention that we had within OATS. The basic building block that it has, you may have seen the word trellis before. Early days of us being involved with AgGateway, it was under the brand the Open Ag Data Alliance. And so within the ag industry, it's called OATA, Open Ag Data Alliance. Within the specialty crop, fresh produce industry, it's called Trellis. But it's basically the same thing. The idea behind it is we defined a standardized API for automated movement of data. And what automated movement of data turns into is really like an engine for microservice architectures that cross company boundaries. So instead of just within us, we actually have things and events that we need to trigger on the other side, and they have things and events that need to get triggered for us. And so that fundamental thing lets us solve some of these data sovereignty problems in ways that we get traceability without transparency. So we're all kind of used to this certification process where we have some kind of trusted service provider or data owner that we have some private data, and we have a form we have to fill out for a regulator like the IRS, and I've got like all my receipts and stuff, and I'll pay an accountant, a human being, to kind of sift through all of my private stuff and fill out the entries on the form on the other side, right? So he's sort of my trusted broker, my trusted agent in this case. And I would call that a manual certification process. But the components are still the same. Like the regulator is the guy who has a form that you have to fill out. The form itself is the certification, effectively. The trusted service provider or data owner is somebody that's automating a process for you. He may be doing it manually, but you just don't have to worry about it. And the private data is the stuff that you just don't want the regulator to see. You don't have a choice over whether the regulator sees the filled out form because it's been required by the regulator. But you definitely have a choice as to how much of the private data that he sees. And so if we wanted to automate this process, what would a private automated certification look like? We want it to look the same, except the guy in the middle that was manually hand calculating stuff, we want to be a piece of software. We want to have our private data on this side, trusted software code in the middle that fills out the form in a very deterministic, regular way based on the data given to it. And so this doesn't really change any of the trust requirements in from the original manual process, because if I gave my accountant bad accounting data, he will process that in a deterministic way and produce a bad certification out the other end. I have to legally sign off that the data I'm giving you, I am certifying as being correct. But then the regulator wants your certification and all the aggregate things that get computed from it into the form. So to do this, the code itself has to be trusted by both the regulator and the data owner. The regulator needs to know that the correct code ran on the data set, right? So he's sort of happy if instead of an accountant looking at it, a software function looks at all of your expenses and receipts, categorizes them all, and spits out an IRS form, right? But he just wants to know that you ran that code and not the code that always spit out that you never had taxes to pay or something like that. That he wants to know that's true. And then as the data owner, you want to know that this code that a regulator approved doesn't have something in it that is going to suddenly like see my tax returns on Fox News tomorrow morning or something like that. So those are the two levels of trust we have to get out of the code that's going to be run. So remember, the way blockchain solves this problem is they have things called smart contracts. A smart contract is that blockchain that we had with all the traceability labels. What if instead of traceability labels, we put actual code inside of those things? So the code goes in, it's immutable, it can't be changed, and then I push data up to another one of those nodes, and when essentially each of the nodes has the code and it says, hey, whenever data comes up in this chain somewhere, run this code on it. So when I run that code on it, it'll be very deterministic. Every node in the network will run the same code in the same way, and they can verify that when I take that data and I run that code on it, I get that answer every single time. But in order to do that, you have to have the code and the data in the thing that we all agree as a shared database, because we're all constantly auditing it, trying to prevent bad guys from getting bad data into the overall thing. And so essentially they make this all public and immutable, which in my opinion defeats the purpose of trust transformation, right? We're not transforming any trust, we just gave everything to the regulator. Now, you can get around some of these things by encrypting the stuff that goes into the chain, okay? So unless you have the key, you can't decrypt it. And you know, a lot of those cryptography problems end up saying like breaking the encryption is the equivalent of like the green electron that I told you before. They're really hard. That's the technical version of it, but the human version of it is you had a disgruntled employee somewhere that like left and took one of the private keys with them and told the world your password was password, and now there's a database with a bunch of data in it that is publicly known by everybody and you can't take it down. Like, it's there forever, and it was encrypted at the time, but now everybody knows the password, so there's nothing we can do about it. So the immutability is great for distribution and auditing and all those kinds of things, but it's not awesome for sort of mitigating when those kinds of problems take place. So the way our version of this, an oblivious smart contract, would do it is that Trellis defines the standard for how the code in the middle can go to any arbitrary platform that has a certain kind of private data that's looking for and find it. And then how it can go and fill out the correct form for the regulator. If you don't have that standard API, that standard way that I can write the code, or at least 5 or 6 standard ways, let's say, so that when the code runs somewhere, it's actually the regulator can verify one set of code and it can run at 100 different places. If you don't have that, it doesn't work. But if you do have that, then suddenly we can actually conceive of doing this process. So the code in the middle, we say, is an oblivious smart contract, and I'll get into the trust levels of it in a second, but the basic idea is we can, in some situations where it's needed, we can certify that the right code ran, and we can also certify a hash of the data that it ran on, so that if I have a legal challenge later, or the IRS auditor comes back out to my place and I need to produce the documents that gave me the passing grade in the end, I can do that, and they can validate, oh yeah, he hasn't changed these are the documents that they were when they made the thing. But the OSC itself, the oblivious smart contract, gets the data via Trellis, runs the deterministic code on it that the regulator would have approved, and it produces the private automated certification. Now in this picture, it looks like it sends it to the regulator. Almost every use case we have so far, that's not what happens. What it does is it makes a certification for you and puts it back in your own data storage. So that means you can run it as many times as you want to see if you're in compliance before the regulator shows up. And once it's run, this is one of the really nice things, once it's run, you are no longer subject to the whims of a human regulator. You ran the code, it said you passed, it was approved by them. This is how that's supposed to work. And so that's the way it works in the manual situation too. That was one of our key design goals here, was that in the manual situation, the IRS agent doesn't know when you have the accountant come out and look over your books, right? You don't need this automated system that causes the black helicopters to show up without your knowledge. You need something that can run and let you know we have a liability here, we have something going on, and that's what this allows you to do. So how do we then prove that the correct code was run and that the result is provably reproducible? Well, I already said the hash of the input data. All the data that came into it all gets a running hash tallied of it within the trusted software code, and that gets included in the form that gets output. And the way that we know the correct code was run, that's a really cool thing called Intel SGX software guard extensions. Anybody ever heard of these things before? Is this kind of new to everybody? Okay, so actually it's in the computers that you have if it has an Intel chipset. They were trying to solve a different problem than what we have here, but it turns out to be a horrible solution for the problem they were trying to solve and a fantastic one for this one. So we got it in everybody's computers anyways. The problem they were trying to solve was most of us run our stuff on Amazon's cloud or Azure's cloud now, right? And so that means, yeah, it's in a VM, and the VM is reasonably protected from the other VMs running on the same physical machines. But all this stuff actually does run on the processor at some point in time. Your data is unencrypted inside the registers on that processor and in memory at some time. And there are a lot of things called side channel attacks that I can have another VM, and I can actually figure out what was going on in the processor when yours was running. And so the idea of SGX was, hey, can I actually get some kind of a trusted enclave, a trusted place to run my code, so that even if it's at an untrusted location, I can guarantee that it got run correctly and nobody was able to see it and nobody messed with it. They pretty well solved the problem of nobody messing with it, but they didn't solve the problem of nobody being able to see it, which is one of the coolest hacks I've ever seen in my life, to be honest. The way they do it is the section of the processor, these special instructions that run these things inside the enclaves, how should I put this? They share the cache, the same cache that the rest of the applications do. And so the reason you have a cache in a processor is that if you get a piece of data for an instruction from the processor itself, it doesn't take very long for the electrons to actually travel there, right? I mean, light travels about a foot per nanosecond. And the actual switches in there can run at essentially the clock speed of the processor. But I can't have a whole lot of that. I start getting a lot of that, and it takes up too much space. So you get just a few of those on the processor that are essentially one instruction access. And then I move beyond that, and I can get some stuff that's slightly farther away on the chip. It takes longer to access, but I could have run 100 processor instructions while I'm trying to go get that one thing out and bring it in. And then if you go to memory, it's 1,000 processor instructions, or sometimes 10,000 processor instructions, and I'm just waiting on this one thing to come back from memory. And that's not even hard drive. If you go back to the hard drive, you're talking millions and billions of instructions that are lost. So they cache these things. They say, hey, if you access that memory location already, you're probably going to access it again later. And so what that means to your program is it runs faster. That if it accessed this thing once, when it goes and gets it again, it's already right there, and you get it right away in one instruction. So the hacks against Intel SGS essentially run a separate process on the same machine. They go access a very defined set of memory locations, and they time how long it takes. And then the trusted thing gets switched in. It runs and accesses some stuff in memory, and then your thing gets switched back in again, and the bad guy accesses the same stuff, and he times how long it takes now. And so he then knows all the stuff that came back really fast must have been a memory address that the trusted enclave accessed. He doesn't know what's in it. He just knows he accessed that particular piece of memory. And from that information alone, they were able to derive the AES encryption keys that were used running inside of the enclaves. They could actually break the encryption and figure it out solely from the timing of, or from the knowledge of which particular memory addresses they were using. It's fascinating. And they made a tool that you can just run it yourself. It's got AI and everything baked in. You download it and click the button, and you can do it. I'm just like, why don't we spend our time on more fruitful things? But anyways, that was an aside. That was one of the coolest things I've ever seen. You wouldn't think that was possible, but it is. So it means that when you're running the code in an untrusted place, there are some side channel attacks that you can't really guarantee that the code didn't get seen by somebody else, or the data didn't get seen by somebody else. We don't have that problem. What we have is the data owner trusts the place he's running the code. He doesn't care if there's a side channel attack because he's already in an environment that holds his data in a database somewhere. So if the guy's going to try to figure out the data, why don't we just try to guess his password to MySQL or something, right? It's much easier to tackle that than it is to try to do these other cache timing attacks. And so what we have is essentially this disconnected process. The regulator needs a signature from one of these chips that guarantees that the code that they thought was run. And then the only way you could have produced one of these signatures is if you're capable to crack open an Intel chip, not screw it up, because they've got a lot of safeguards in there that essentially it blasts the chip apart if you take the chip, the casing off, and then probe the silicon to try to figure out exactly what this private key that's sitting in this password sitting inside of this processor is. And you know what? If you can do that, it was a whole lot easier just to send bad data to the software code than it was to probe that chip. So essentially, all of the security problems with Intel SGX don't apply here, but we get all the benefits that Intel is effectively guaranteeing you that the correct code was run, even if the guy on the other end wasn't willing to guarantee that he ran the correct code. So what we're left with then is, in my opinion, what the correct approach to the solution is that blockchain is a tool in the toolbox to be used to solve cross-company certification problems. So we split the kinds of oblivious smart contracts up into 3 different levels. So the first one I call owner attested. This is essentially, we're doing business with someone we trust already. We just have a business process that we need to automate, and I don't need to ask them to send me all their private stuff. I just need the true or false. Like, I'll give an example in a little bit, but like we produce a sustainability report. They have a sustainability report. I don't need them to send me all their underlying data. I just need them to send me like total amount of energy produced from renewable sources. That's all I need. Like, I don't need them to sign this off and have a third party verify it and so on. Like, we just want to automate some processes. And so that's what an owner attested one is. We just write some code. And the difference is they're not shipping their data to the code that I'm going to run on it. I'm shipping the code that's going to run on it to the data. So I eliminate the privacy concerns, at least beyond what you're going to report to me. I can't kind of eliminate that concern. If you don't want to make that in the report, then there's no way around it. Trust level 2 is enclave attested. So it's that exact same model, but instead Intel's also going to sign off on this from its own processor in a way that then you can validate later that it was run, that this code was run on a valid Intel chipset. Like AMD and others have their own versions of these things. And then trust level 3 is the one thing you can't get from the first 2 are time and order guarantees. You could put a timestamp in the private automated certification, but the guy's clock could have just been wrong on his machine that did it. There's no way to guarantee that he gave you the correct time. So you need some non-breakable external system that can provide you proof that at this point in time, this thing actually existed. But in order to keep the model that we wanted, where the regulator doesn't know when you're running all of these things to see if you're compliant, then we have to have a way of doing that anonymously. That essentially, if I give you the form, you can check the blockchain and say, oh yeah, all right, this proves in the blockchain that the thing that made this form was run at that time. But if you just had the blockchain, you couldn't figure out that it was me running it. So here's an example. Let's take nitrogen, phosphorus, potassium per field. So like I said, I had cows, so the Indiana Department of Environmental Management wants this information from me all the time. And so one way that I could get that to them is, well, let's say in my trellis store, I had my field boundaries, I had GPS tracks or just like hash marks of loads, of how many loads of manure from which sources went to which fields, and the lab manure sample results. So it said how much NP and K was in each one. And I kind of hand compute this right now and tell them how much nitrogen I put on that field this year and how much phosphorus. Well, they would probably be perfectly happy if I could automate that. They'd sign off on a piece of code that said, yeah, this code knows how to find those things if you have them and calculate how much total nitrogen you applied to the field and spit out the report that I need. And it automates it for me. I don't have to do it. And I get a check mark that when I run it, I know the regulator is not going to change their mind when they get here because they signed off on the code. So that's an example of trust level 1, that they're trusting me to give them that data anyways, right? I mean, there's days that is hash marks on a piece of paper in a notepad. If I don't keep the data, nobody else has it. So I'm the only source of it. So in a sense, I am inherently signing off as this is the correct data. I just have computed a deterministic aggregate. Another one is that cross-enterprise sustainability report that I talked about. Is just that essentially I'm just going to ship this code to you. You run it on your own internal stuff for your own sustainability report, and then it'll make the thing that gets shipped to me, and then I can compose these things together across the supply chain. Now we'll move up to trust level 2. So this is where we don't necessarily trust everybody. So this would be a sustainable fishing certified catch area. So I met one of the guys from the Global Dialogue on Seafood Traceability a couple years ago. And he said they had this problem that they have polygons defined in the ocean of where are sustainable catching areas. Like you're allowed to catch fish from this spot. But to certify that, you kind of need me to give me all the GPS locations of where you caught your fish, and then I make sure they're inside the polygon. And so they made some boxes that are kind of hard to hack. That they have one of the examples I saw was pretty cool. It had like a NFC card that you would just tap on the box every time you caught some fish, and it would log the GPS locations there. And so you get this log of them. But if you're a fisherman, where you caught your fish is kind of your secret sauce. You don't want to ship that off to some public database so everybody else can go run in on your catch, right? So we need this zero knowledge proof kind of a thing where I can get a success failure out the other end. I can get true, this was caught in sustainable areas, but I don't know specifically where it was caught. And so in this model, that's really easy to do. A piece of code that can check if all the points are inside of a polygon is not hard. So we write that piece of code, the regulator signs off on it. But in this case, this guy, it's harder to fabricate the GPS locations themselves than it is to just say, oh yeah, I caught it in the right place. So we've sort of made it slightly more difficult. The boxes that are kind of certified to say, hey, I'm a certified producer of a box, and I'm certifying that he tapped the card at the right places, that adds to this. But we still don't necessarily want to trust him because he, by default, would want to make things that all say that I caught them in sustainable areas, whether I did or not. That's the whole point of the certification. And so that's where the Intel SGX stuff comes into play, is that he can have his stuff within any kind of a system somewhere and run the software code on an Intel SGX platform, and it'll include an Intel signature that the regulator can verify later that said, I did indeed run not the code that always says success, but the one that makes sure all the points were within that spot. And then so what it spits out is this lot number, success, failure, and we solve the problem of leaking too much information. Then the most complex one, but it's my favorite, because it brings, mainly because I had to think about it for about 3 months. I call this organic mass balance. So the organic food industry has this problem that of fraud. Everybody knows this. They're trying to cut down on the fraud, but essentially it's a certification problem, right? That let me break it down to you this way. Let's say I even went above and beyond, and I had a regulator come out to my farm and tell you that I could produce 10 tons of organic apples. It looked like that was what my harvest was going to be, or they certified that's what I harvested, 10 tons of organic produced apples. I had all the documentation, and I took that PDF document and I mailed it off to 4 different guys and said, I can send you each 10 tons of organic apples. And they'll all say, yep, certified, but I just shipped out 40 tons of apples. I grew 10 of them the expensive way, 30 tons the cheap way, and they all got counted as organic. And, that's bad enough. But when you get down into kind of feedstuffs and things like that, like if I produce if I have an entire ship of soybeans coming from China certified as organic, and it all gets fed to supposedly organic pigs, and then we find out the whole ship wasn't organic, all the pigs now are no longer organic. Like, this is a problem. There's huge ramifications of the fraud itself throughout the industry. But we have all of these weird knowledge leakage problems in any sort of a certification process, right? So the simple thing is, well, let's all make a shared database, and we will dump the, when this guy wants to buy and sell stuff, they're going to have to register that transaction in the shared database, and they'll all get certified. And then I know that nobody, when I go and check it, nobody has subtracted the 10 off of this guy's ledger yet. But once he sold it the first time, his balance is now 0, and now I know that he's trying to double dip. But the problem is that releases the information we said before that an industry of middlemen doesn't want to release. It releases a whole lot of stuff like who I bought from and who I sold to. It tells the guy that I'm selling to how much product I haven't sold yet, which is a really bad thing if I'm trying to negotiate a price. And it also tells me actually how much stuff the other guy has bought. I know he hasn't bought very much stuff yet because they haven't logged hardly anything into this shared database. It's like, how can we solve this in a way that doesn't leak all that information but still guarantees to certify it? So this is where blockchain has to come into play. We need this kind of third-party place that we know we can put some anonymous stuff, but we can't fake it. So the basic idea is in the Trellis store of the guy that's producing the apples is going to be a ledger. JSON document that just has, it was initiated by an increase of 10 tons by a signed auditor. And so his balance went up by 10 tons of apples. And every time he sells some, it needs to decrease by that amount. But, and when it gets to 0, like the smart contract in the middle, the oblivious smart contract, it needs to tell the buyer, hey, he doesn't have any more to sell you. But what it can't say is how much does he have left. It just has to say, I'm trying to buy 5, is 5 available? And if it is, then it'll say true. But the goal is this guy gets to keep the ledger in his own data store and do his own stuff with it, but then run an Intel SGX supported piece of software that verifies the ledger doesn't break. So the thing we had to add to that was effectively a one-time use key. That the top 2 are really easy. Just check the signatures of the seller and buyer, make sure they're legit, check the ledger balance, that it's greater than the quantity we're looking for, and do a couple other validations. But the biggest thing is there's a one-time use key, a private key, a password, that the guy selling it gives to the guy that's buying it. And that thing essentially gets marked as used in the blockchain. And so once he's used that thing, he can't use it again, and it's linked together in his own private document. So once he's used it once in the blockchain, the next time this smart contract runs, it will not allow him to double use the one-time use key. So that's how we can guarantee that he's not double dipping through a blockchain, but still not leak any of the information we didn't want to leak and just say success failure. And it's kind of cool too because these things are composable. Like I can transfer stuff from my private ledger to your private ledger and you don't have any of the stuff on my private ledger, but you got 5 more tons of organic apples. This happens a lot in the produce industry that like you have a shipment, your neighbor has a couple of pallets that you can add in to make it go because you didn't have enough and we still need that to work in real situations. We just had this is a really great example of how we can do this kind of a thing. Like, I don't know if you guys have ever tried to deal with inventory stuff across like a large organization, like a co-op of co-ops or something like that, that if you have a broader scale thing that essentially is your supplier and he's trying to sell things and he could sell things better if he knew how much inventory you had on hand, but because you negotiate with him sometimes, you'd rather not tell him how much inventory you had on hand than enter Oblivious smart contract. Oblivious smart contract is he knows he has a sale and he's got to come up with like 20 pallets of Roundup, or something in 2.5 gallon jugs. So he's essentially writing into a bunch of the different suppliers' trellis stores, hey, I'm looking for 20 tons of this, can you supply this? And their smart contracts reply, yes, I can, or no, I can't. They don't say, yeah, but, or no, I only have 18. They don't tell you how much is left. They just say, I could actually do that, and then the transaction's done and we're good. So that's another example of where we can use those kinds of things. This is just an example of, there's actually some code that monitors this whole process for you in your trellis store, and this is actually the architecture itself that kind of shows how those things go together. So this is in a paper that is actually coming out soon, and we've actually got one large-scale enterprise customer that's implementing it at the moment, and there's a couple more kind of waiting in the wings, but I have to say, of all the things we talk about, this is the one that seems to generate the most interest with folks. That almost everyone has this problem of how do we certify something without releasing our secret sauce, but do it in an automated way. And to the best of my knowledge, this is the only solution for that kind of a thing so far. So I have a few minutes left, which is not normal for me, so I can take questions now. And I have a mic if anybody has them. Most everybody's still awake too, so I know there's questions. Yeah.
Where do we start?
Okay, question was, where do we start? Can you be more specific? So I'm a fan of building things from the ground up and not from the top down. And so where you start is we have a particular partner. That's where our other ones are at. We have a partner that we want to do a thing like this. And so we do that once. And in that process, we figure out what schemas are defined, what schemas aren't defined, what standards are there, what aren't there. And that all gets published as part of that process. And when it's done, we have one implementation that solves this one problem in a nice, clean way. And it's also essentially published, because it's open source, as a proposed standard for how you would solve that kind of thing in other places. And so, I don't know of any better way than just one at a time. So that's my best answer. But yep, get a use case and map it out. But I think the main reason I wanted to give this talk to you guys is that this should be a tool in your toolbox. Okay, like as you're thinking about these problems and this comes up, you say, hey, that actually is a great solution for this, and you've looked at other places and it doesn't quite do what you want. It's nice to know that this is possible. So it took us a while to figure out it was possible. Yeah, thanks, Scott.
The tutorial URL available?
Is the tutorial URL available? Yes, I think we're going to put this up. I don't know, are the slides going to go up, Jim? Do you know? Well, yours are up. All right, we'll put my slides up too. If you want the easy way to get to it, Trellis FW is the Trellis framework. So if you go to github.com and you search for Trellis framework, Trellis FW, you'll get all the stuff that's associated with Trellis, and then you will see blockchain tutorial right there. And look at that, there's a link. So you click it and GitHub pages serves, and it doesn't work. Trellis FW GitHub. I missed the I, look at that. And that's it. So the code's all there in that repo, and GitHub pages just serves the thing. So it's self-contained. It's not like sending this back to a server somewhere and churning through stuff. It just runs in your browser. It even runs on your phone. I was very impressed with that. my phone can chug through those things too. So it's very hard to see all the stuff going on, but it's kind of fun to swim the ocean of chains. So yeah, that's what we put it up for is, hey, if you guys ever have to tell somebody about what blockchain is, like that, I don't know of a better example than that race, where you actually see them guessing those numbers and racing through and seeing that. So, and I can't take all the credit for it. This guy right here had kind of the smallest inkling of the beginning of this, and he didn't have the racing and the stuff, but that's where I got the idea from. So, other questions? No? All right. Well, thanks for coming, guys, and I'll be around.